So space weather is a term that's used to describe the changes in the space environment around the Earth, mainly between the Earth and the Sun and in the area immediately around the Earth, where conditions are quite variable, in the same way that the atmosphere is variable on timescales from minute to minute and hour to hour, day to day, and when we get into climate, as we start getting longer than a few years or so, then there's space weather, which is the short-term variations from minutes up to hours, days and weeks, that things in the space environment around the Earth change. So we're thinking about magnetic fields and space plasmas, so electrically charged particles in the space environment.
And where do these things like space plasma come from?
Well, plasma is the fourth state of matter. So if we take any material, melt it into a liquid, we can then boil it into a gas. We can then start to heat it up and break apart molecules into atoms. Then you can strip electrons off atoms, and eventually you'll end up with a soup of electrically charged particles, electrons and ions, or electrons and protons. And so that's a plasma. So the sun is really a big ball of plasma to most intents and purposes. But also the sun is a big source of plasma in the solar system. So as the solar wind leaves the sun, so this is kind of like the smoke rising from the bonfire of the sun, the hot gases leaving the sun behind, because they're plasma and they're electrically charged, they drag with them the sun's magnetic field out into space. So that's one big source of plasma, that's the solar wind. And you can measure that right up to the edge of the solar system. But there's also, closer to the Earth, at the top of the Earth's atmosphere, gases like oxygen and nitrogen get ionized, they get bombarded by ultraviolet light, they get broken down, and the area around the Earth fills with plasma from the atmosphere.
And how is Earth protected from this space weather? Because I understand that other planets that don't perhaps have this kind of protection aren't suitable for life. So how are we protected?
Well, here on planet Earth, here at ground level, we're protected by two things. There's the atmosphere. So the atmosphere, first of all, keeps out most of the radiation from the sun. So, okay, if you go out on a hot day and you don't have sunblock on, some UV is gonna send you pink. But generally, most of the radiation from space is absorbed by the atmosphere long before it gets to the ground. But actually, it's kind of a two-tier defense system. So the Earth has a strong magnetic field, and that magnetic field stops the solar wind plasma before it can get at the atmosphere. And so if you look around in the other parts of the solar system, on Mars hasn't got a strong magnetic field. So the solar wind could get right down to the atmosphere. And so originally, Mars probably had a much thicker atmosphere. So shortly after it was created, Mars had a thicker atmosphere, but that's been eroded away over billions of years because Mars hasn't got a strong magnetic field.
So it's the magnetic field that protects the atmosphere that protects us? Basically,
yeah. So if you're worried about life on Earth, biological risks, then actually it's the atmosphere that protects us, and the magnetic field of the Earth protects the atmosphere. But space technologies and some technologies on the ground are actually a little bit more vulnerable than the biological risk. So actually there's a whole different series of risks, not just the biological risk.
How does the magnetic field actually protect us from the solar wind? How does it deflect it?
Well, the plasma is sort of stuck onto magnetic field lines, if you like. The best way to think of it is that plasma, the particles of plasma, tend to stick onto field lines just like beads onto a string. And so as the solar wind is moving out into space, you can think of it in two ways. You can either think that the plasma is moving away from the sun and it's dragging with it the magnetic field onto which it's attached. So that might be like thinking of moving the beads which are threaded onto a piece of string, then the string follows the beads. The other way to think of it is that the magnetic field is moving and is taking the plasma along with it. But either way you look at it, the plasma and the field move together. But just like the string and the bead analogy, if you've got two separate pieces of string threaded with different coloured beads, it's very difficult to make the beads hop from one piece of string to the other. You actually have to cut the strings and tie them together into some new kind of configuration to do that. And there's a process called magnetic reconnection, which actually couples the magnetic field in the solar wind onto the Earth's magnetic field, allowing plasma to move between the Earth and the solar wind.
How do we know how the solar wind affects the magnetosphere? How do we go about examining it?
Well, going back hundreds of years, people have been able to see the northern lights. But hundreds of years ago, people didn't know what the northern lights were, the aurora borealis, and there are lots of legends about them being spirits and ghosts and all that kind of thing. Well, if you bring it forward to the sort of start of the scientific era about 150 years ago, where we were making measurements of the Earth's magnetic field, then astronomers noticed that when there was a lot of activity on the sun, the Earth's magnetic field was quite variable. And actually some of the biggest disturbances ever seen or ever recorded scientifically were by Victorians, astronomers connecting solar flares and outbursts from the sun with geomagnetic disturbance. And then you fast forward, of course, once we hit the beginning of the space age, then the first spacecraft that left our atmosphere started to measure the solar wind. The first spacecraft to leave our atmosphere, we found the radiation belts with radiation detectors on satellites. So very quickly it became apparent that the space around the Earth wasn't empty in any way at all. It was full of stuff from the sun.
And you mentioned the aurora. I suppose that's a kind of visible evidence of the way that the solar wind interacts with our magnetosphere. How is it formed? What is it?
Okay, so the northern lights or the southern lights, so there's the aurora borealis and the aurora australis. The physics is identical, so we tend to think of the northern lights because we're a bit biased, but it can be either way. They are formed by the fact that energy leaks from the solar wind into the Earth's magnetic field, or into the region of space governed by the Earth's magnetic field. And that energy is actually energy and momentum, which is leaking out of the solar wind and into the plasma around the Earth. That energy accelerates plasma, so particles with mass that are actually in the vicinity of the Earth. So it's quite interesting because the energy is coming from the solar wind, but most of the material, the particles, are actually plasma from the top of the Earth's atmosphere originally, probably. It's very difficult to know because you can't paint them pink and put labels on them from where they originate. But these particles, once they've got some energy, they tend to bounce along magnetic field lines from one pole to the other, north to south. And then some of them actually can leak out of that sort of trapped, that region, and leak out and escape into the top of the Earth's atmosphere, where they crash into atmospheric gases, usually atomic oxygen. So the stuff you're breathing in and out with every breath actually gets bombarded from space by high-energy electrically charged particles. And it just causes it to glow in the same way the gas in a neon lamp will glow. The gas atoms will obtain a bit of energy in a collision, just like any other collision, a collision between two cars, for example. Momentum is exchanged. The gas particle doesn't really like having that much energy. It's been promoted from a very ground level up to an excited state, and the only way it can ditch it is to throw out a photon of light, or even perhaps a couple of different photons. But basically, it wants to get down to a low energy state, and and depending on the energy state transitions that result, you get different colours of light that emit, either visible or X-ray or ultraviolet.
So the radiation belts, where you've got these particles bouncing back and forth between the poles, what are they and how do we study them?
So the radiation belts are formed because electrically charged particles, which are threaded onto field lines, they actually tend to spiral around the field lines they're threaded onto, and they bounce from one pole to the other because they're generally repelled from regions where the field's getting stronger. So as they approach the North Pole, all those magnetic field lines, you imagine drawing a map of the Earth's magnetic field line, they're converging to the polar region. The field's getting stronger, so the particles are reflected away from that and bounce back to the other hemisphere where they bounce back. And so particles just tend to oscillate from one hemisphere to the other, and they can take anywhere from a few seconds to several minutes to bounce from one pole to the other. Now, some of these particles, they can get scattered, there can be collisions, interactions with waves on the field lines, a lot of mechanisms which aren't very well understood at the moment, and they can actually leak out of this trapped region. It's almost like a bottling effect, and they can leak out the top of the bottle, and that's how they get into the top of the Earth's atmosphere, and some of them will cause the aurora. Now, the radiation belts were one of the very first things ever discovered in the space age. So sometimes they're referred to as the Van Allen belts. A very famous physicist, James Van Allen, discovered them at the end of the 1950s on one of the first rockets ever launched into space. And it's quite interesting. We still don't fully understand how particles in these radiation belts get up to such high energy that we kind of call them radiation. We recognize them as radiation. They're electrons, beta particles, if you like. So we still don't fully understand that. So we don't know quite how they fill up and how they empty and what makes them very active, what makes them quiet. And so there are, for example, there's an upcoming mission later this year, which NASA are launching, the Radiation Belt Storm Probes, which actually a pair of spacecraft are going to be flown through the radiation belts every orbit to go through and sample them and seeing how they change, how they fill up, and try and understand the physics by actually making measurements in situ inside the radiation belts.
And what will it mean if we can understand the radiation belts and also the Earth's magnetic field in general a bit better?
Well, the radiation belts actually sit in a part of space around the Earth. They're kind of donut shaped, they surround the Earth. And by coincidence, that's the part of space also where if you put a satellite, it goes around the Earth just once every 24 hours. So that's where geostationary satellites are. Now, modern day, we rely on satellites so much. Even going to the supermarket, buying a lottery ticket, going on a train journey, there are so many ways that satellites are involved. And it's important to understand that some of these radiation effects can actually damage the sensitive electronics on satellites. So they can be damaged, disabled, or their operation can be impaired. So as we become more and more reliant, apart from just understanding the basic physics of what's going on, just for the interest and the wonder of knowing what goes on, we really also need to know the environment in which our satellites and all the infrastructure our society depends on, how it changes with solar activity.
And therefore, if we know more about this sort of level of geostationary orbit in these radiation belts, we might be able to change the way that we make our satellites to make them more able to withstand.
That's right. So satellites can be manufactured which are more radiation hardened. They can be manufactured or even so that they are just perhaps have a few more error checking routines on board perhaps, or operated in a more safe way. They can be, for example, you wouldn't launch a spacecraft into a particularly full and active radiation belt area. And there are even technologies now that are looking to try and drain the radiation belt. So actually using experiments on the ground to put radio waves into the radiation belts that actually cause the particles to leak out and therefore empty them. So there's all sorts of really interesting physics going on associated with the radiation belts.